Okay, so to recap what happened during the previous 3 days. So the first day, we started describing what Boolean function analysis is about, and we saw the proof of the analysis of linearity testing. Then the day before yesterday, we explored the KKL theorem, which is the first result in Boolean function analysis. So I think 88 or something. We started doing the proof. So we reduced the KKL theorem to the level D inequality. And then we reduced the level D inequality into this moment bound for low degree functions. And then yesterday we proved this moment bound using hypercontractivity. And I tried to link hypercontractivity to many other things in math, and probably most of you lost me, but you got to hear some buzzwords. So maybe in the future it will resonate. And today we're going to shift gears and possibly, and definitely today and tomorrow, I will claim some statements. This proof we won't see at all, just because it's a bit too long. So this program is, my goal is to prove Bourgain's booster theorem, and hopefully I will be able to push it back for tomorrow. So we'll start our discussion with the problem of threshold of graph property. Okay, so this is one of the most famous applications of Boolean function analysis in probability theory. The other one being stuff interpolation, which I don't know much about. And to address this problem with graph thresholds, we will have to introduce biased Fourier analysis. And then, depending if we go really fast, which hopefully won't be the case, then I might be able to present this application to Erdős-Corrado theory. Okay, and if not, maybe we'll have time for it tomorrow. And if we won't have time for it at all, then too bad. And then maybe today, probably tomorrow, we will start discussing this global hypercontractivity, which is this a new idea. And by now it's not so new, it's like 5 or 10 years ago. That Noam Lifshitz came up with, which is a way to address the failure of hypercontractivity in biased spaces. And using this, one can give an understandable proof of Bourgain's booster theorem. Okay, so this is just a quick plan. So you don't know what any of these terms means. So maybe this description was a bit meaningless, but hopefully it will make sense as we go on. Okay, so we start by describing these problem of thresholds of monotone graph properties. Okay, so we start by defining what we're interested in. So graph property is a property of graphs. Okay, so far I haven't said anything, which is invariant under isomorphism. Okay, so some examples. Containing a triangle being connected, having precisely k edges, and so on, and some non-example. The degree of the first vertex is 5. Okay, so this is not invariant under isomorphism. But we're never interested in properties which are not invariant under isomorphism. This will be very artificial. Okay, so if you're interested in, I don't know, properties of random bipartite graphs, and for some reason you are intent on using the GNP model, then maybe you're in this non-example level. But this is silly. So usually, really, the properties of graphs that you're interested in are graph properties. Okay, so anything reasonable you can think of which doesn't mention names of vertices is a graph property. Now, a graph property pi is monotone, it's what you think, if whenever G satisfies the property and H contains G, then H is in the property. Okay, and here there is a caveat. So what's really happening is that pi is a sequence of properties, one for each number of vertices. So pi 1, pi 2, pi 3, da da da. And in each of them, we fix the vertex set. I mean, it doesn't make any difference because this property is invariant under isomorphism. And when I say H includes G, so H and G have the same vertex set, but H could have more edges. Okay, so often in computer science, in TCS, it's very common. I'm saying like a circuit, and I really mean a family of circuits. Okay, and here I'm saying a graph property, but it's really it's a graph property for each number of vertices. And usually there's some assumption that these properties are related somehow. Okay, but actually in the proofs, it won't come up. It's something that bothered me when I was your age. But it doesn't bother you anymore, so if it bothers you, then just will disappear as time goes by. Yeah, so okay, some examples of monotone graph properties containing a triangle. Let's add containing at least 10 triangles. It's also monotone. Being connected. This is not monotone, having exactly k edges. Yeah, being an expander is having a spectral gap. Also, I guess it's potentially not monotone, depending on how you define it. Yeah, but most, though not all, most properties we are interested in are monotone. Okay, and here are some classical results in the random graph theory. So the probability, so I'm assuming that everybody here knows about the Evler-Shreni GNP model, but I will just briefly explain it in case you forgot. So we have n fixed vertices, and we add in each edge with probability p independently. So confusingly enough, in the Evler-Shreni papers, they use a different model. They fix a number of edges. So calling it the Evler-Shreni random model is kind of wrong, or anachronistic, or whatever, but still we'll stick to this name. So the probability that G and C over n contain the triangle okay, so this tends to 1 minus e to the minus c cubed over 6. Okay. Another example, the probability that G n log n, this is natural logarithm, plus c over n is connected. It tends to e to the minus c. Okay, so this is for constancy. If c goes to infinity, then this will go to 1. If it goes to, if it's little of 1, this will go to 0, and similarly here. And this follows from these statements anyway. Okay, so although this is not the topic of this class, and although maybe some of you have seen it, let me just briefly explain to you where these funny formulas come from, because I think random graph theory is a nice area, although I've never actually worked on it. I proved one result, and after the referee said, yeah, maybe this is known, I figured out it was known. So this is my contribution to theory of random graphs. But yeah, okay, so why is this thing true? So you can compute the expected number of triangles. Okay, so expected number of triangles in G n C over n. This is n choose 3 times C over n cubed, right? So it's a probability that particular triangle is P cubed. And this is very, very close to C cubed over 6. Okay, and now if you think of it, then different triangles, they typically don't share edges. So the different events for containing a triangle are quite independent. Not completely, but roughly speaking. And this is enough to imply that the distribution of the number of triangles is Poisson, with this expectation. So this is a probability that this Poisson variable is positive. And this is actually how the proof goes. So now I gave you enough ideas and you can do the proof. It's a bit tricky, but not too much. And now that I told you the proof, you could also, if you want, calculate the limiting probability of this event containing 10 triangles. Okay? Now, how about connectivity? So there's some calculation that you can do, and for this value of p, then it's unlikely that your graph contains a connected component of size between 2 and n over 2. Okay, you do some kind of first moment argument, some union bound. It's pretty easy, but we won't do it here. You can do it at home. So the only obstruction to being connected is having isolated vertices. Okay, now what is the expected number of isolated vertices? So this is n, and the probability that the specific vertex is isolated is 1 minus p to the power n minus 1. And this is, roughly speaking, n times e to the minus log n plus c, which is e to the minus c. Yeah, and again, so if you look at two vertices, then they only share a single edge. And the probability of an edge is basically 0. So these events are almost independent. So the limiting distribution of the number of isolated vertices is roughly Poisson. And now we want there to be 0 isolated vertices, which is why we get this funny quantity. Okay, so if you've never seen these proofs, now I basically told you all the ideas, and now you can do it at home. Okay, now I claim that there is a big difference between these two properties. Okay, so let's see why. So we do this kind of plot of the probability, let's say, of containing a triangle. So this will be the probability of containing a triangle. Okay, so this probability is going to be monotone. Yeah, this follows from the monotonicity of the graph property. If you want to prove it formally, you can do it by coupling. We'll actually see it. So if you look at things from the scale of 1 over n, yeah, so 1 over n, 1.5 over n, 0.5 over n, then it will be something like, qualitatively, it will look something like this. I mean, maybe the shape is wrong, but there will be some non-trivial graph here. So for every point that you choose here at this scale, there will be some number which is strictly between 0 and 1. And it just follows from the formula. But if you do the same for connectivity, so this is the probability that G and P is connected. So now the right scale is like log n over n. So now let's do 1.5 log n over n, 0.5 log n over n. And now the way it's going to look is like this. If you look at the limiting distribution. So it will just be a jump. Okay, so we call this force threshold. And this we call a sharp threshold. Okay, and just to define it formally, so we let PC, this is the probability, or rather is PC of n is the value such that it's probability that G and PC of n satisfies the property is exactly C. Yeah, maybe C is the wrong choice, but whatever. Okay, so we know that this exists for any non-trivial monotone graph property. Okay, non-trivial means it's not like the empty property or the complete property. And the reason is that the probability that G and P satisfies the property is some kind of polynomial, and it's increasing. So it has to pass through any real number between 0 and 1. Okay, so a property is force if P 2/3 minus P 1/3 is theta of P half. Yeah, so this is the critical probability. This is the probability where the property holds its probability exactly 1/2. And this we think of as like the width of the window where the action happens. Okay, so for the property of containing a triangle, the critical probability is some constant over n. And the critical window also has width, like 1/n. Whereas for connectivity, the critical probability is roughly log n over n, but the width of the window is like 1/n. So the threshold is sharp. Sometimes you ask about one-sided sharpness. So there are some properties where the behavior right of the threshold is different from the behavior left of the threshold, but we won't care about this. Now, for some reason that I don't completely understand, people in random graph theory, they really care about this. And to the best of my understanding, like I haven't talked to an actual random graph theorist, if your threshold is sharp, then it's easier to locate it. Okay, because if you found the probability P, where the probability that G and P satisfies the property is not like super close to 0 or to 1, then you're basically at the threshold. Okay, so this is true if the threshold is sharp. So you would really want some criteria that tell you that the threshold is sharp. And the way that this criteria look like is that they say, okay, if a graph property is coarse, then blah. So if you can prove that for your property blah doesn't hold, then the threshold is sharp. And I'm going to show you an example soon. Okay, so this area is known by the name of sharp threshold theorems. The first sharp threshold theorem was proved by Yuval Filmus, who was my kind of informal supervisor back in the day, like before he met me. And in an appendix to his paper, then Bourgain had a different sharp threshold theorem, which is much easier to use, and the proof is shorter. But maybe the proof is shorter because it was written by Bourgain. So he optimizes for the length of the proof. And eventually, Ahmed Hatami came up with like an if and only criterion, some criterion that is equivalent to the graph property being coarse. But this criterion is hard to state and it's hard to work with, so nobody actually used it. But it was important enough. It was published in, I think, like Annals of Math or one of these very good journals. So, like a yeah. Okay, so now I'm going to state to you this Bourgain's booster theorem that we're going to hopefully prove tomorrow. And then we try to see how all of this business connects to Boolean function analysis. Okay, so this will be Bourgain's booster theorem. So suppose phi has a coarse threshold. Then there exists a P, which is between this P 1/3 and P 2/3. Okay, so this is suggestively looks like a single number, but it's actually a function of n. This is how you write things in TCS. So this everything here is a function of n. And a fixed graph H on order 1 vertices. So although I call it fixed, for every n, it could be a different graph. Okay, such that the probability that G and P union 8 satisfies the property is at least the probability that G and P satisfies the property plus omega 1. Yeah, so to make this statement confusing, I've removed all the n's, but you should really add them everywhere. So everything here is a function of n.
What is the union here? Is it disjoint union or?
No. So I'm not changing the size of the number of vertices because this won't make any sense because like this graph property is really it's a family of graph properties, and there's no reason for pi n to have any connection with pi n plus 1. It would be completely arbitrary. So I'm just adding the edges if they're not already there. Yeah, so if you want to be more formal, then this would be like hn and pi n, en, en, and yeah, so this is the less confusing statement, but I just want you to be ready. If you ever read a paper in TCS, you won't see the ends, but it's the same meaning. So it's good to get used to it.
But Hn has O1 vertices.
Right.
So
yeah, so the number of vertices does not depend on n. So the number of vertices is going to depend on the coarseness of the threshold.
So is it like when you have GMP, do you select more subset where you have?
Right. Yeah. And the size of this is going to depend on the constant here. And it can only be made explicit. Like when we do the proof, it will all be explicit. Okay, so I'll give you an example and then we pause for questions. Okay, so the property of containing a triangle is coarse. And indeed, it satisfies Bourgain's booster theorem. And in what way? If you add a triangle, any triangle, then it boosts the success probability, like it boosts the probability of containing a triangle all the way to 1. Yeah, so it was something between 1/3 and 2/3, and we boosted it all the way to 1. Now you can say that this is kind of boring. Maybe it's not representative. So let's take the property of containing 10 triangles. Then you can still put a fixed triangle, and it will still boost the probability of containing at least 10 triangles. Okay, by some amount that you can calculate. So these properties are coarse. And now connectivity, we said the obstruction to connectivity is having isolated vertices. But these isolated vertices, there are going to be only a few of them, and they're going to be like randomly distributed on the graph. So if you put a fixed subgraph, like this subgraph H that you're going to paste in order to try to boost the probability of connectivity, it will probably not touch any of these isolated vertices. So it actually won't help you to connect the graph. And this way you can prove that the property of the connectivity does not have a coarse threshold because of this. And if you're careful, then you can even get like I think like a log n factor here. So although I've studied everything with constant coarseness, you can actually, everything here is quantitative, so you can get even super constant non-coarseness. So I think you get the right log n factor up to constant factors. Yeah, other examples is being not tolerable, also popular. Yeah.
Is the converse kind true as well?
Yeah, I don't think so. Yeah, we can try later thinking of an example. I mean, it must be easy. So this is not an if and only if. If you want an if and only if version, then there's this Khatami's theorem, which is somewhat cumbersome to state. Yeah, but this would be. I mean, I never thought about it, but I'm sure there is an easy example. Maybe take the union or the intersection of two properties. That's usually what works. Yeah, so that's not supposed not to be an if number. Yeah, and kind of the go-to example is like Hamiltonicity, which is harder to argue about, or containing a perfect matching, being not K-tolerable. So these are the examples where it's already non-trivial to prove that the threshold is sharp. And it's even harder to compute the threshold. So then this theorem is useful. Now, if we're, yeah. So it was like 1 or 2 years ago where some physicists won a Nobel Prize in physics for computing thresholds. So people in physics also care about this. There's Giorgio Parisi. So the physicists have this method for predicting thresholds. They think of it as a way of finding thresholds. So they have something that they call a proof, which is some sort of argument which mathematically makes no sense. And then some people, they spend like an exorbitant amount of time to formally prove these things that the physicists knew 20 years ago. And they come up with proofs for some special cases, which are like 100 pages long. But then they verified this physical proof. So that's like you wonder whether formal proof is really the right answer always. Like if the physicists, they know the answer and they have something that they call a proof, so why can't we accept this as a proof? Like what's the big deal? Why do we care so much about being formal? It's not like our proofs are always correct, right? They contain mistakes. So it's a point to think about. Okay, so any questions about what we've seen so far?
So this union is edge union on the same vertex set. And
Right.
the subgraph is not induced subgraph and subgraph. Right?
So if it's induced, then the property won't be monotone. Yeah, so here it's
So when you take a union, there's kind of possibilities that maybe there exists some place where you can place H in some.
No, but you have to fix the
Or-
location. I forgot the condition.
Can you add it at H anywhere?
You can add it any way you want, but it's going to be at a fixed location.
So from 1 to some.
Right, and so the condition I missed is we are assuming that the critical probability is very small. Okay, and this means that so you put this graph H, and probably all the edges were missing because the probability is small. Yeah, now it doesn't have to be like the first K vertices, but it has to be a fixed location. Otherwise, connectivity would also satisfy this because we know that it's very likely that there are only few isolated vertices, and if you knew where they are, then you could fix it. Yeah, so you don't want to do it. In the proof, you will see where this comes up.
So may I interpret this Western theory as some kind of so every coarse threshold property can be interpreted as having a fixed subgraph H.
Yeah, I mean, in a sense. So this roughly says that these coarse properties, they are local in some sense. But for the exact sense, you need Khatami's theorem, which is this if and only if criteria. And it's a bit more complicated. Yeah, so if we find this counterexample to this being an if and only if, then you'll see why it's a bit complicated. But yeah, the idea is that these properties are local, whereas connectivity is a global phenomenon. So you can test whether a graph contains a triangle by looking at some specific edges, but connectivity you need to check many things. It's also related to what happens in percolation, where you try to construct show decision trees that decide certain properties. And if you succeed, then this implies something about the noise sensitivity of the property. Yeah, so this locality is eventually related to degree, which, as we've seen in this level inequality, it really influences the way the functions behave. So this is sort of what is going on. Any other questions? Okay, so now we put this aside, and I hope not to get to this theorem today. Hopefully we'll only do it tomorrow. What instead we will do today is we will try to connect all of this to what we've seen so far. Okay, and we'll do it in some kind of slightly awkward order. So we will start by trying to see what the existence of a force threshold mean. Like, what can we deduce from it? And this will naturally lead us to this bias Fourier analysis, which I guess you can also find other reasons to do. Okay, so this section will be about force thresholds and Russo-Margulis formula. Yeah, so I think this was proved independently in the East and in the West, and that's why it has two names. Okay, so suppose phi has force threshold. So I want to say that if you look at, let's call this function, I don't remember what I called it in the notes. Let's call it alpha of p. So I want to say that if a threshold is coarse, then this implies a bound on the derivative of this function. So alpha of p is the probability that G and P satisfies the property. Okay, so as we go between, so by assumption, alpha of P 2/3 minus, let's say, n minus alpha of P 1/3 of n. So this is, I want to say, this is at most k times alpha p half of n. Okay, so there should be a point here where the derivative is small. All right, so there exists a p in p 1/3 n, p 2/3 n. Sorry, this is its most. This is 1/3. Okay, such that alpha prime of p. So this is at most. So it's the difference in the y's over the difference in the x's, right? So it's 1/3 over this p 2/3 of n E 1/3 of n, which is order 1/e half of n. Okay, so I hope I got the mean value theorem correctly. If not, then I'll check the notes. So from this assumption, we get that somewhere on this curve, there's a point with whose derivative we can bound. And in the formulation of Bourgain's boosted theorem, we promise that there is some probability where something happens, and this is this probability, so it's going to come from here. And there's a spoiler that we relate this to total influence. This is the connection to Boolean function analysis. Okay, so this is the first step, and now to actually see the connection, and we're going to find a formula for this thing. This is this Wolfson-Margulis formula. So the next step is formula for alpha prime of p, and so just to remind you that alpha of p is the probability that G and P satisfies the property. Okay, so somehow when we take the derivative, then we take something which will look familiar from Boolean function analysis, and this is why I think people made this connection in the first place. But I guess I have to ask Ehud for the actual history. Okay, so this formula for alpha prime of p, I won't reveal it. We will find it step by step. And this is this Wolfson-Margulis formula. So at least Wolfson's paper was called on the approximate 0-1 law. So a 0-1 law states that if you have a property which can be described in a reasonable kind of logic, for example, the first order logic of graphs, then for every constant p, the probability that G and P satisfies the property, it tends to either 0 or 1. So that's why it's called the 0-1 law. Okay, and here is the 0-1 law holds approximately. Yeah, I don't know the entire story behind this, but you can see it's also related to threshold phenomena. So these graphs that I showed you is like an approximate 0-1 law. Anyway, so I think this is, he was trying to understand this, like his paper is short, but I have never actually read it. Okay, so alpha prime of p, this is the limit as epsilon goes to 0 of alpha of p plus epsilon minus alpha of p over epsilon. Okay, so I mean, we all know calculus. And for convenience, we'll think of the limit from the right. I mean, it's equal to the limit from the left because this alpha of p is just a polynomial. So we think of epsilon as being positive. And we're just going to calculate it. So there are several ways of doing it. Like if you like machine learning and the chain rule, then you can do it using the chain rule. But I like doing it, yeah, the way that I'll show. So we want to calculate this. So we fix p and we think of epsilon as something very, very small, infinitesimally small. And we want to know what's alpha of p plus epsilon minus alpha of p. Okay, so alpha of p plus epsilon minus alpha of p. Yeah, I didn't say, but phi is a monotone graph property. So this is the probability that G and P plus epsilon satisfies the property minus the probability that G and P satisfies the property. Right? So the way we're going to tackle this is we're going to couple G and P and G and P plus epsilon. Okay, so this coupling I show in the very first lecture on random graphs, when I teach random graphs. But I don't think every textbook does it this way, so it might be new to you. So this is something that's unrelated to Boolean functions, and you might find useful. So for the coupling, for every vertex, we're going to sample a uniform 0, 1 random variable. So this will be for vertex 1, vertex 2, vertex n. And we're going to put two thresholds. So this would be at P. And this would be at P plus epsilon. So this is not to scale because like these two lines are really at the same place, right? Because epsilon is very small. Okay, so the probability that this uniform 0, 1 value is below this threshold is exactly P. So if we take all the, sorry, I said these are vertices, but these are really edges. So it's 1, 2, 1, 3, up to n minus 1 n. Yeah, so the probability, so if I choose all the edges whose value is at most this orange threshold, then I just get G and P. And if I increase the threshold to the pink line, then I get G and P plus epsilon. Okay, so we can call the graph corresponding to the small threshold G, and the larger graph we will call H. So H is everything, including G. So this is equal to the probability that H is in pi minus the probability that G is in pi. But H contains D. Okay, so this is the same as the probability that, or rather the expectation, yes, probability that H is in pi and G is not in pi. So I obtain H by adding possibly some edges to G. So I run the probability that G is does not satisfy the property, but once I added these additional edges, then now it does satisfy the property. So this is the same because H contains D. This is the coupling. Okay, and if you're not sure, then if you do this with expectations, then it will be maybe clearer. So this is the expectation of the indicator of H in pi minus the indicator of G in pi. And the indicator that H is in pi is always at least as the indicator of G in pi. So when you subtract them, you get either 0 or 1, and you get 1 precisely in this situation. Now, how do you obtain H from G? So most likely you won't add any edge. Okay? So the probability that you add any edge at all is at most n epsilon. This is just the union law. Okay, now what's the probability that you add a single edge? So it's epsilon minus order of epsilon squared. Okay, so because we're going to divide by epsilon, then we only care about stuff that happen, events that happen with probability epsilon. If anything happens with probability epsilon squared, then it will get lost in the limit. Okay, so if we had no edges, then I mean it's not the case that G is not in pi and H in pi. So really the only interesting case is if we add one or more edges. So this is okay, so we start by the probability of adding exactly one edge. So we go over all ij. So it's the probability that H minus G is a single edge. . times the probability that G is not in pi, and G plus the edge is in pi. Okay, and the probability of adding two edges is like epsilon, at most n squared epsilon squared by unit bound. So we kind of don't care about this. Okay, and this probability is epsilon minus order epsilon squared. Okay, so to summarize, we got that alpha p plus epsilon minus alpha p is epsilon times sum over all possible edges. So probability. So yeah, the way we're going to write it is yeah. So let's G something from G and P. So G with the edge removed is not in pi. And G with the edge added, so this is this A. Is in pi. And plus some error term of epsilon squared. Yeah, this is not maybe not exactly what we wrote there, but it's the same thing. Okay, this implies, so now if we divide by epsilon and take the limit epsilon goes to 0, so alpha prime of p, the sum over all the edges, whatever it's written here. Okay, and this is equal to okay, where F is the indicator of pi. Okay, so we got this by dividing by epsilon and taking the limit epsilon to 0. And then in terms of the indicator function of the property, then this thing is the same as f of this thing being 1 and f of this thing being 0. So it's the same as the difference being 1. Okay, so this thing is 1 if and only if this thing is 1. And otherwise, if it's not true, it's 0. This is because property pi is monotone. Okay, so let's circle back. So we computed this derivative by using this coupling, and kind of because epsilon is small, then the difference between the two graphs G and H is at most a single edge, and it's a specific edge with probability roughly epsilon. So when you divide by epsilon and take the limit when epsilon goes to 0, then you can just ignore everything else. And so you get only these events. So if you add the edge, then it's in the property, but without the edge, it's not in the property. And in terms of the characteristic function, then you're just taking the expectation of f where you add the edge minus f where you remove the edge. Then I'm writing it this way because, I mean, we've seen this kind of expression before. This looks something like influence. Okay, so eventually this is going to be related to influence. This will be the punchline after we define influence in this set. Yeah, if you don't like this coupling, then you can also do the computation using the chain rule. The chain rule for derivatives. But it's the same thing. So we've done the proof of the chain rule in this special case.
I'm a bit confused then. The big omega square there, does it come from the case that h minus g has at least two edges?
Right.
Okay.
Yeah.
Okay.
Yeah, so kind of what's happening here, and it's also what you see in, I guess, if you prove the chain rule, is because epsilon is small, then it's most likely that you'll see exactly 0 differences. And then the next likely thing is that you see exactly 1 edge in the difference, and then 2 edges. So you get Taylor expansion. Yeah, which if you don't like this argument, then the other way of doing it is so you want to use the chain rule, but this is a bit awkward. So you want to have a different variable for each edge. And then you can apply the chain rule and you'll get it. Now I give you some hint, and using this hint, you can do this proof yeah, without this coupling. But I think this coupling is not.
We differentiate one, then do we get two influence of two edges?
So
Then and like third, fourth, and
I think so. Yeah. So this doesn't usually come up, but this seems. Okay, so let's just edit here. So alpha prime c, this is sum over all. Yeah, so here I did everything for graphs, but you can do it for any function. It doesn't have to be a graph property. So alpha I station of x equals 1 minus f of x equals 0. Where f is the characteristic function of the property, and mu p is the product distribution where every coordinate is equal to 1 with probability p. Okay, so this is like the generalization of G and P to situations where you don't have any graph. Okay, so if you couldn't follow the proof of this Lewis formula, it's really not this difficult. Maybe I made it more difficult than it should be. But it's kind of applying the chain rule. And we applied the chain rule using this coupling, but you don't need to do it this way. What you end up with is this thing, where this is the station of f of x, where x is according to mu p. And f is that's a function from 0, 1 to the n of 0, 1 is monotone. And this mu p, I'm writing here, so we have everything on the board. So mu p of x is p to the sum xi, 1 minus p to the sum 1 minus xi. So example, each point is probability p, and x0 is probability 1 minus 2. Okay, so if you couldn't follow the proof, I think I messed it up a bit. Then, well, this is what we get in the end. So, and here I'm writing I rather than ij because really everything makes sense, even if it's not a graph property, if it's just any kind of function at all. Okay, so now we switched terminology, and instead of having a graph property, a monotone graph property, we just have a Boolean function which is monotone. So if you change the input by adding ones, then the output can only change from 0 to 1. And now instead of G and P, I have this mu P, which is just the same kind of idea, but without the graph. And everything else is the same. Actually, this Bourgain's booster theorem, it doesn't mention graphs. It's still beyond graphs. Okay, so any questions about any of this?
Formula is true for all product variables.
Yeah, so it's even true if you have a different probability for every coordinate. I guess in that case, you need to kind of change them in the right way, so that you get, like in general, you have something here which depends on how you change the probability. Yes. And the fact that the threshold of this property, it doesn't have to be a graph property, is coarse, just means that the derivative is somewhat small. It's not very small because this 1 over p is large, but it's somewhat small. Yeah, so really the main reason I did this proof is because I wanted to show you this coupling thing, which you might find useful. Even if you do something completely different. So coupling is this technique that if you know about its existence, then some of these things that you have no idea how to show are easy. Okay, so I said that this is supposed to look something like influence, because we saw expressions like this. And now I'm going to make it precise. Okay, so now we're going to generalize this Boolean function analysis to this mu p measure. Okay, so maybe the original motivation was this sharp thresholds, but you can also do other things with it. For example, you can prove stability versions of the Elbers-Corrado theorem. Okay, and I might have time tomorrow to explain the connection. Okay, in percolation also, I mean, percolation is essentially random graph, random subgraphs of not the complete graph. So also they care about this mu p measure. Yeah, so there are many reasons to study it. Now we've seen one, so hopefully now you have lots of motivation. Yeah, so we want to do Boolean function analysis, but with respect to this biased measure. Okay, so this will be biased Fourier analysis. And the idea is so we want to generalize everything to work with respect to mu p. Okay, so when we discussed the Boolean function analysis, and we had the inner products, norms thrown around, and everything was under the assumption that the Boolean hypercube was being considered under the uniform measure. Okay, for plus minus 1 to the n, and here's 0, 1 to the n, but this is not the difference. I mean, this is just superficial. What's really different that here everything will be with respect to mu p. So if we discuss the norm of something, it will be an expectation with respect to mu p. Okay, because essentially this is because here x is drawn according to mu p. So in order to use this ideas from Boolean function analysis, we need everything to be with respect to mu p. So for example, the Fourier basis was an orthonormal basis with respect to the uniform measure over the cube. But it won't be orthonormal anymore if you use the mu p measure. Okay, so the first step is find Fourier basis which is orthonormal with respect to the inner product is defined like this. Okay, and if we find such a basis, then we would use it to replace the basis functions that we used to use, these ESs. And then at least the basic setup will still work. Like we will be able to define Fourier coefficients, and we would have like the Parseval's identity and all of this stuff. Okay, so this is the first step, and it's an easy step. Okay, so I'll just tell you the answer, and I'll explain why this is the answer. So the answer is, okay, omega s. So this is the new basis functions. They're going to depend on p, but I'm not going to write p anywhere. It's going to be understood. Okay, this is the product over s xi minus p over square root of p1 minus p. Okay, so maybe you don't see what's happening here, but this is what we do to make this thing have expectation 0 and unit variance. So we subtract the mean is p, and we divide by the standard deviation. Okay, and why does this make sense? So if we take the inner product between omega s and omega t, okay, then this is the product of I in asymmetric difference t of xi minus p over square root p1 minus p times j in s intersection t of xj minus p squared over p1 minus p. Okay, now what is this equal to? So if s is not equal to t, then there would be such an I which is in S symmetric difference t. Sorry, this is expectation. Yeah, this is expectation of everything. Expectation. Yeah, so this unit product is the expectation over this entire product, and we can bring the expectations inside. Yeah, I'm doing it a bit quickly because we've seen it in the unbiased case. Okay, so it's just the same thing. Okay, so it's really equal to the expectation of this entire product. And to compute it, we separate it into the different factors and we bring the expectation inside. Okay, now back to what I was saying. So if S and T are not the same, then there will be some I in the symmetric difference. Okay, so we will have one of these terms. Now, because I subtracted the expectation of xi here, then the expectation of this term is 0. Okay, so I remind you, so mu p is the measure where, so if x is mu p, then the probability that xi is equal to 1 is p, and the different indices are independent. Okay, so in particular, the expectation of xi is equal to p because it's either 0 or 1. So when I subtract p, then I get 0. The expectation is 0. This is why I subtracted p, and this is how I designed this basis. So this entire thing is equal to 0. So if I have any of these factors, then this inner product will be 0. Now, what about this? So the expectation of xj minus p squared is the variance of xj. And you can compute it, it's p times 1 minus p. Okay, so when I do the division, then this is equal to 1. And again, this is by design, so this is how I chose the definition. Yes, so I subtracted the mean and I divided by the standard deviation. So I get something which has mean 0 and variance 1. Okay, so now if S is different from T, then I have at least one of these factors. So this product is equal to 0. And if no, then I only have these factors, and it doesn't matter how many of them do I have because each of them is 1. So this thing is just equal to delta SP. So this basis is orthonormal. Yeah, so question about that. So what's really happening here is we chose this basis for n equals 1, where there were two basis functions, the constant 1 function, and this x1 minus p over square root p1 minus p. And to get the basis for 0, 1 to the n, we just take products. So this is what we call tensorization. Okay, and if this this thing is orthonormal for n equals 1, then using this construction, we get something which is orthonormal for any n. Yeah, this is why we like product spaces so much, because to understand them, it suffices to understand each of the factors, which is very easy. Okay, and with this, we can define, using this, we can define Algebraic notation. So Fourier expansion, Fourier coefficients, and so on. Okay, so we can write any function f as the sum s subset of n of f type of s omega s. So this also is a Fourier coefficient which depends on p, but I'm not going to write p because it would be a bit cumbersome. Okay, F hat of S is the expectation of F times omega S. We have Parseval. So the norm squared, it's like I promised, this is with respect to mu p. So this is the same as the expectation of F squared. It is the sum of all the squared Fourier coefficients. Okay, so this is true for exactly the same reason why it was true in the unbiased case. Okay, so I'm not going to repeat the proof. This is just true for any orthonormal basis. And also we have F hat at the empty set. So this is still the expectation of F, but now with respect to mu p. Yeah, so all of this is true for exactly the same reason. This is because omega empty set is the constant one function. Okay, so this is a basic setup of the very basic setup of this bias Fourier analysis. And now on Tuesday we saw influences, and on Wednesday we saw noise. So now we're going to extend the definition to this setting. Okay, so we'll define the ith influence is phi of f. We just take the Fourier definition. And in a moment, we will see how it relates to other types of definition. So it's possible to define this Li operator and it would still work, but there's some issue of normalization. Okay, and the Nord operator, P of all F, let's say from S all to the S, F hat of S, omega S. Okay, so this is the same definition using the Fourier formula. Okay, and both of these things, you can also give them a definition the way we defined it in the unbiased case. Okay, so we'll address this in a moment. But for the noise operator, then if you recall, when we defined T of f at the point x to be the expectation of f of y, where y was this noisy version of x. And how was this noisy version of x defined? So for each coordinate with probability rho, we fixed it to the current value, and otherwise we resampled it. And you can use the same definition here, and you'll get the same formula with the same proof. Okay, so there's no need to repeat it because it's just the same. So now you can go back to your notes, and you can check that everything still works. Yeah, just the same proof works. So if you recall, we defined T rho using this noise distribution N rho. And we had two definitions. One was more explicit, and the other one was this one with the resampling. And this resampling definition, you can just use it as is. You don't need to change anything. And you can do the same calculation, and you get the same formula. So if you don't like defining things with formulas, then you can define it this way. Okay, we defined this noise operator for the sake of hypercontractivity, and we'll go back to this in a minute. But first, I want to connect this influence business to what we see here. Okay, so if you recall, you can define influences using this Li thing. Here we're going to use a different definition, which is di. So di f at the point x. And this is the derivative with respect to xi, which is f of x where I gets 1 minus f of x where I get 0. Okay, so I mean this is the same thing as is written there. Then, and this equation holds because everything is still multilinear. Okay, so we want to express this in Fourier terms. Okay, so it will be better for us if we squared it. So this thing is either 0 or 1, okay, because f is monotone. So for monotone f, then this formula states that alpha prime of p is sum of I times the expectation of DIF squared. Okay, so here it's written DIF, but because it's either 0 or 1, I can square it. Okay, and which is I of to norm of DIF squared. Okay, so now I want to relate DIF. I want to relate the Fourier expansion of DIF with the Fourier expansion of f. And you'll see that this is like roughly the ith influence. Maybe it's not surprising. Okay, so we want to compute DIF. So because this di is linear, then we only need to compute it on these functions omega s. Yes, so what's di omega s? Okay, so this is omega s when you set I to 1 minus omega s when you set I to 0. Okay, so if s does not contain I, then this is just 0. Okay, so if I is not an s, then di omega s is equal to 0. Okay, so what if I is equal to s? So di omega s. Okay, so this is a product of j in s minus I of this xj minus p over square root p 1 over p. Okay, and now, so this will be common to both of these expressions. Now we will have 1 minus p over square root p1 minus p minus 0 minus p over square root p1 minus p. Okay, so this is the contribution of the factor corresponding to xi, where here it's equal to 1. We substituted xi equal to 1. And here we substituted xi equal to 0. Okay, and this is equal to omega s minus I times 1 over square root of e1 minus p. And I guess the other way of seeing this is because it's just a derivative with respect to xi, and then you immediately get this. But people who don't like derivatives, you can do it this way. Yeah, so this is not a complicated calculation. And as a consequence, so DIF, now we want to write the Fourier expansion. So this is the sum over all S containing I of F hat of S divided by square root of P1 minus P omega S minus I. Yeah, which is very similar to this formula with the for the ith influence. Particular, so this is sum over I 1 over P1 minus P sum I in S at f of S squared, which is 1 over P1 minus P times the total influence of F. Which I remind you is just the sum of all the influences. Okay, so up to this normalization factor, then you can define the ith influence using this DIF. And there's also a definition which is more like this LAF where you don't get this factor. But you have to change it a bit because instead of you define LAF by flipping a coordinate, and instead you need to resample it. And then you still get some normalization factor, but it doesn't depend on P. Yeah, but you can think of the ith influence as related to the experiment of sampling all the other coordinates and then checking what happens, what the influence of this coordinate is on the function. So it's the same kind of idea. There's some choice of normalization, and we choose it so that we get the same Fourier formula. So this is maybe the less confusing choice. Okay, so this is influence of F over P1 minus P. Okay, so we did all this calculation, and we see that, okay, so here we have P hat and here we have P, but these are roughly the same, okay, up to some constant factor, because the property is coarse. So you can think of P and P hat as the same. Because we assume that P is small, then you can forget about this factor 1 minus P. So what this thing really means is that if the property has a coarse threshold, then there's this point P, which is between P1/3 and P2/3, where the total influence is constant or is bounded. Okay, so we did all this very long calculation, and this is the end result. Okay, so I'll summarize it. Okay, so let's erase this. So this is the conclusion of everything we've seen today. So conclusion. If F has a coarse threshold, then there exists P such that expectation with respect to mu P of F is in 1/3, 2/3, and the influence of F is order 1 with respect to mu p. Okay, so this is the connection between force thresholds and Boolean function analysis. So having a force threshold is essentially the same as having constant total influence. Okay, so before pausing for questions, I'll just mention what happens if p is constant. So there's a theorem called Friedrich-Hunter theorem. So this is back in the standard setting where everything is unbiased. So if f is a function from ±1 to the n to ±1, and epsilon greater than 0, then there exists a function g from ±1 to the n to ±1, such that g depends on 2 to the order influence of f over epsilon coordinates, and f and g differ its probability at most epsilon. Okay, and now if we think of epsilon of influence of f as constant, and of epsilon as constant, then what this means that if f has constant total influence, then it's close to a function depending on a constant number of coordinates. Okay, something we call a junta. That's the stand up for the junta in what, Argentina, somewhere in South America. Okay, and we're not going to do the proof, but the proof is very similar to the KKL theorem, and you can find it in the notes once it will be accessible to the outside world. Okay, and this is true in the unbiased setting, and it's also true for any constant p. And generally speaking, whatever is true for p is equal to half, usually is also true for any constant p. But it's not true in this case. So, for example, for the property of containing a triangle, it's of course has a quark threshold. So we've just shown that there is some p where this holds and the influence is bounded. But the property of containing a triangle is not close to anything which depends on the constant number of coordinates. So it doesn't look like a quota. It looks like something else. So this proof of Friedrich-Hunter theorem, you can think of it as the same as the proof of KKL. There are some differences, but they're pretty minor. So something must break. Okay, and this something is hyperconductivity. So hyperconductivity is true for constant p, but it's not true when p is little of 1. Okay, and this is easy to see. We'll see tomorrow. It follows from the level D inequality. So the level D inequality implies if you look at constant degree functions that the norms are equivalent, but it's a very easy calculation that we're going to do first thing tomorrow to see that this fails when p is small. So hyperconductivity is false. We'll see tomorrow how to handle it, what replaces hyperconductivity, and this will enable us to prove Bourgain's Fonta theorem. Booster's theorem. So the proof of Bourgain's Booster's theorem will be quite short. It'll be similar to the proof of KKL. What I won't show you is the proof of this thing that replaces hyperconductivity, because while it's not difficult, it's a bit too long, and I don't want to memorize. Okay, so we're going to see this tomorrow, and if we have any time left, then we also see a proof of the Erdős-Colorado theorem using bias Fourier analysis. So that's it for today, and if you have any questions, then now's a good time. Questions?
So if the total influence of F is bounded by a constant, so does it mean that the F is not spiky?
F is not.
Not spiky.
Right, so it means something about F. Yeah, so it's, well, we'll see what we get tomorrow. Yeah, so if P is constant, then all your intuition it still holds. For some constant F, there are some issues. Yeah, but if you look at the delta function, I think we'll still have high influence. Or if you, let's say, look at the parity function, it will influence the high influence. Yeah, so everything up to today where we knew like years ago. So what I'm going to talk about tomorrow is relatively new stuff. So if you stay in this for tomorrow, like we don't want me to know too much about what you've done today, then you'll get to know something which is actually new and exciting. For you, it will be hard to appreciate why it's exciting because we don't know the basic stuff, but yeah, you just have to trust me that it's exciting for the experts. Okay, so see you all tomorrow.